So for this last video, we're going to be looking at some different competing reactions that might be occurring when we're doing these SN1 and SN2 reactions, and we're going to take a look at how do we determine if a reaction is proceeding via a SN1 pathway or an SN2 pathway. So first let's look at some of these competing reactions. These first two typically just affect SN1 reactions. So something that can happen is something called a hydride shift. And so it's literally, as the name implies, a hydrogen is shifting through a molecule. And so we can see here, right, we have this starting compound, right, with a chlorine on a secondary carbon, and clearly we have a polar protic solvent, so an SN1 reaction should be happening, but the bromine, right, our nucleophile, ends up on the other carbon somehow. So how does this happen? So, right, it is a hydride shift, but we'll go ahead and look at the actual pathway that's taking place. Right, so we know that we have our chlorine leaving, and we are now left with, right, our carbocation intermediate. Secondary, which is fine, it prefers to be tertiary, which is kind of the point of this next step, this next hydride shift. Right, so we know we have a hydrogen here, and so what actually happens is we end up with a hydrogen shift that takes place. Right, so the electrons on this covalent bond shifts over to this carbon here. And so the result of that is now, right, that once carbocation now has that second hydrogen in place, and this carbon here is left without a hydrogen, so it is now a tertiary carbocation. Which means we can do our SN1 nucleophilic addition. You notice here I had sodium here next to bromine. This was just, right, the counter cation. It's not doing anything in the reaction. It's just there to stabilize the negative charge of bromine. So you might see some of these counter cations like sodium, potassium, and some of those other group 1 metals that might be stabilizing negatively charged anions, right, these nucleophiles. Right, and so simply we have the bromine, right, attack the tertiary carbocation there, and we end up with our products. Right. Of course, I should probably have chlorine here. Didn't do that before. And what ends up happening at the end is, we can just put the sodium and chlorine atoms together, right, to form that ionic bond. But this is the process that takes place during this hydride shift, right? We're making a secondary carbocation into a tertiary carbocation, which is much more favorable, right, remembering our reactive intermediate rules. And so essentially the same thing takes place during this next competing reaction called a resonance rearrangement. And so as you can imagine, right, with chlorine leaving on its own, as you would do in an SN1 reaction, we are left with a secondary carbocation next to a double bond, right, which we know can undergo resonance. And now we're left with, again, a tertiary carbocation, which much prefers, right, which this reaction much prefers than having a secondary carbocation. So again, same process, where we have bromine come in and attack the tertiary carbocation to get our products. And again, that is to say that these competing reactions occur when there's a chance for a more stable carbocation, right? In each case, we had a secondary carbocation get transformed into a tertiary carbocation through either resonance or a hydride shift. So the next type of reaction that can occur is something called an intramolecular reaction. Right, so inter, right, molecular means between two molecules, So an intermolecular reaction, like we've been seeing, occurs between two or more molecules, and an intramolecular reaction occurs within a single molecule. And so what's happening here is we have our alkyl bromide, and we have our negatively charged species here, which, as we remember right from the last video, this is not a good nucleophile, right? It's too bulky. So instead, it acts as a base. It acts as a base instead. Again, because of that steric hindrance, it's too bulky, right? It can't come in and get rid of the leaving group here. So what we end up seeing is, you'll have to redraw this in order to see the hydrogen coming off. But what we see is the oxygen species here removing that hydrogen to get our negatively charged oxygen species here. And so what we've kind of done is we've kind of made our good nucleophile, right? We have a primary carbon, right, a primary alkyl halide, which is perfect for an SN2 reaction, and we know that because we have DMSO, so we know this goes through an SN2 pathway. And so what happens, because this is an intramolecular reaction, the oxygen on the molecule ends up being the thing that attacks that carbon center there and kicks off bromine as a leaving group. And so what we end up getting is something that looks like this. We get this sort of ring structure here. And we have to be kind of careful when we're doing reactions like this, because we need to go through and make sure we have all the right number of carbons. So we have 1, 2, 3, 4 carbons and 1 oxygen, right? This oxygen made that bond with the carbon here. So we have our 1 oxygen in the middle of this ring and our 4 carbons here. So we know we've made the right structure. Right, with Br minus as our leaving group that came off, and terbutanol as the conjugate acid here from that first Bronsted acid step. So when we're doing these intramolecular reactions, again, just kind of be careful when you're making the final cyclic structure to make sure you have all the carbons counted up right, you have the atom in the right position in the ring. So just be careful and double count all your atoms going through these intramolecular reactions. So finally, how do we determine whether an SN1 or SN2 reaction is happening? We've kind of discussed this already through some of these videos and in lecture, but to sort of list out the rules here a little more clearly, we know what we have an SN1 favored if we have any formed carbocation that's really stabilized, meaning we'll probably end up having a tertiary or secondary electrophile. The solvent is polar protic, right? Water, methanol, etc., which will stabilize the carbocation intermediate, and only poor nucleophiles are present, right? Because if we had a good nucleophile, we might end up going through an SN2 pathway, and a poor nucleophile will ensure that that first rate-limiting step, right? Because SN1 reactions are determined by the concentration of the electrophile. Poor nucleophiles will help make sure that electrophilic, or rather make sure the leaving group leaves on a electrophilic molecule. So an SN2 reaction is favored if the electrophile is not sterically hindered, so essentially it is not a tertiary carbon. We have a polar aprotic solvent, right? Acetone, DMSO, DMF, acetonitrile, right? Because a polar solvent will end up stabilizing a carbocation intermediate. So we want a polar aprotic solvent, which doesn't do as good of a job as that. And we have strong nucleophiles present, right? And this is important because we know that SN2 reactions are a second order reaction, which we know is dependent on the nucleophilic concentration and the electrophile, right? So we have a stronger nucleophile present, we know this will help promote that reaction. But in general, right, to make it a little more succinct, tertiary substrates will undergo SN1 substitutions, and primary substrates will undergo an SN2 substitution. The only time you have to really decide whether one is happening over the other is pretty much when we have a secondary carbon, right? And that's when we'll need to look at the solvent, the nucleophile, the leaving group, in order to determine which is happening. And so in lecture, what we'll do is we'll go through these 5 different reactions, right? And we'll kind of take a look at what type of reaction is happening and fill in some of these blanks here, right? Because we're missing solvent in some cases, products in other cases, and reagents in other cases. So we'll go through and sort of determine whether an SN1 or SN2 reaction is happening and fill in some of these blanks in order to satisfy the whole reaction.